Um, I guess I can wait just another minute or, yeah, it looks like there's a couple people still joining, so. All right, well, I'll get started now. So thank you, Shane, for that introduction. So you guys know a little bit about me if you've seen the prior lecture, but just to quickly go over it again so you get a bit of an idea of the background that I come from. This is my dog who loves tennis balls, a better picture than one of me. So I started off with an undergraduate degree in software engineering, and I then got my MD and completed my general surgery residency in Calgary. And I'm currently a computing science master's student in Edmonton here. So my disclosures, no financial disclosures yet. I am academic focused. I have lived pretty much my entire adult life in academia in one form or another. So there is certainly a slant to it. And I definitely wouldn't be able to approach things the way somebody from industry would, for example. And then also, I know I can talk fast and I might breeze over some things that either aren't clear or that I'm glossing over or that aren't familiar to people in the audience. And I know we've historically had quite a diverse audience. So if any of the people in the audience have any questions along the way, please let me know. I'll try to keep an eye on the chat as we go, or feel free to unmute yourselves and ask. Either way. Very happy to talk. Even if you just have comments or kind of random things that you want to chat about, I would love to talk about these things with everybody. So this is the outline of the talk, and I'm going to start by talking about bias. So bias has a couple of different definitions that are salient to artificial intelligence in medicine. Probably the standard definition for bias in artificial intelligence is the mathematical concept of the bias of an estimator. Now, often an estimator is an artificial intelligence model, which would be represented by this mu with the hat on it to denote a prediction. And so the bias is the expected value minus the true value of that parameter. And so in this way, you can determine if a model is making a consistently wrong prediction in one way or another. This is related to, but not exactly the same as, the English or usual definition of bias, which is a prejudice in favor or against something, particularly when it's unfair. This is the definition that I'm going to focus on with regards to this presentation. Because it has to do with a lot of, oh, awesome. I'll let Shane handle that chat question if that's all right. Because it has to do with a lot of recent research and really important advances in AI. So starting off with a case example here from this paper, which I thought was very interesting. In this paper, the authors used a large set of insurance claims data with many thousands of patients, both white and black, and they subsequently used that to predict health costs. This type of model, they used this and created this because this type of model is actually in fairly common usage in the United States, at least. For two reasons. Number one, because it's important for them to be able to predict who is using a lot of healthcare resources, but also so that they can try to improve the healthcare of these patients that can use a lot of resources and potentially improve, cut down on costs. So what they would do, for example, with this type of model is they would create a risk score, and then if you're over a particular threshold for the risk score, in this case it was the 56th percentile, then you would be referred for screening for a particular intensive health program. These intensive health programs are expensive. They can't be offered to everyone, but in a lot of cases, they would improve people's health by being in these intensive programs. If you were past another threshold, this one's the 97th percentile, then you would just be defaulted into the program. You wouldn't be screened. You would just go straight in. And so what they did was they had a look at the characteristics of this model. And at first glance, it actually looks like it's calibrated quite well, even with respect to racial bias. So the median risk, very, very similar in terms of the expected costs out of Black patients versus white patients. And even the top 5th percentile risk, also extremely similar between Black and white patients. But when you break things down based on how many active chronic conditions or comorbidities the two sets of patients have, you'll find that the curve for the Black patients is significantly higher than the curve for the white patients. And so what does that mean? Well, let's say if you held constant and you looked at the patients in the data set who had 2 comorbidities, you would find that the Black patients use less, they have a lower risk score, and so they use less healthcare and insurance dollars as compared to the white patients. So what this means is that Black patients are receiving less care as measured by costs and controlling for comorbidity. And so this isn't something that that is super obvious that you would expect. What the model is doing is it's amplifying existing biases in a way that is tough to know that this is going to happen in advance, and it really highlights the need to think about these things as much as you can in your AI models. This next paper I thought super interesting as well, a different type of bias. So this is looking at bias in the data sets that you get with respect to the hospital that they were acquired from, the data sources themselves. So this model that they created is a classifier for chest x-rays. So what they did was they used chest x-rays in patients from 2 different hospitals. These different hospitals had different baseline prevalence for pneumonia. So one hospital, like for example, it would be like a community hospital that doesn't have super sick patients. And the other one is a very busy tertiary care center that has very, very sick patients. You can imagine that the baseline prevalence of pneumonia might be different in these 2 populations, and indeed it was in this paper. And they found that the model performed quite well, but it performed worse on external testing versus internal testing. So external testing meaning they used data from a 3rd hospital, completely unrelated to the training set, and tested it and found that it performed worse when compared to a data set where comprised of cases from the original 2 hospitals. So when you use your data set to create an AI model, you'd split it up into training, validation, and testing. And your test data set is comprised typically of the same type of data, that you trained it with. It was just set aside at the start. And so that's what I mean by internal testing. So how did they want to explain this? Like, how did they go about trying to figure out what was happening? So they used this. These are called attention maps or saliency maps. It's a type of explanation. I'll talk about explanations and interpretability in a minute. But essentially what it does is that as these numbers get higher, it indicates that this portion of the image contributed more to the positive diagnosis of pneumonia than other places, for example, that are negative. And so the lead author of the study, he talks about these areas here where he's not really sure what's going on. And this is another issue with regards to neural networks, deep neural networks in particular, is the fact that they're super opaque. Like, it's really hard to know exactly what the model is looking at that is contributing to a positive pneumonia diagnosis out here in the soft tissues, but it is. But something that they found consistently is that the models would heavily weight areas that had things like these tags, these labels that say portable, semi-erect, a laterality marker, Even things like the snaps on a hospital gown typically weighted positively towards diagnoses. And so what the authors inferred here is that the model is determining which hospital these patients are from, and is using that to then peg them to a specific baseline and then modify their risk based on the image after that. And like, is this necessarily a bad thing? Well, if you're planning on deploying the model at one of those two hospitals, it's probably okay. It does show that the model is going to learn whatever it can in order to make these diagnoses as accurately as possible, and it's going to use shortcuts if possible. It's also going to be very, very difficult to predict in advance what exactly it's going to do when you're training. So, like, what are some solutions to some of these bias issues? Well, you can start by measuring what you want to measure. So what I mean by that is, for example, in the insurance data set, if they didn't only measure costs, or if instead they measured the health outcomes of patients, you might see that the bias would decrease or go away completely. Because they used a surrogate for that health cost, you can see that patients could have the same amount of cost, but the outcomes could still be not equitable. Another important takeaway of this is that removing sensitive information such as race doesn't necessarily make your algorithm less biased. So in the insurance data set, race never entered into the algorithm, and the model still ends up being biased against Black people. So you can't just hide things and expect that your algorithm will not have bias. Finally, for data, this is kind of a standard refrain in machine learning and many types of AI, in that you should use large, diverse data sets that resemble clinical applications as much as possible. So for that, the hospital chest X-ray classifier, if you're planning on deploying it in 100 hospitals across the country, you should ideally use data from 100 hospitals across the country, or at least more than 2. For testing, so an important thing, do the testing, test it all. There's a surprising amount of AI literature that shows these breakdowns here of the training data, validation, and testing data. And you'll see that they only split it into training and validation / test. There's not 3, there's just 2 data sets or segmented parts of the data set. And the issue with that is that if you do your training and then you check it on the validation set, and then you decide, I think I can improve on that, and you go back to your training set, and then you change some things, and then you check it again and you have a better value. This isn't the validation set that you've done it on. That's no longer representative of unseen data. You're going to overfit on that. And there is a surprising amount of literature out there that continuously makes this type of error. So be careful for that. So that's something important to look out for when you're evaluating a machine learning article. Finally, doing an external test is always a good idea. I predict that if external tests were done for many of the very high-performing AI models that are out there today, we would see efficacy drop significantly. This isn't the case in all of them, and generalizability has become a lot better, especially in the past kind of 2 or 3 years, but still a big issue, and something that you should think about if you're doing AI research. Moving on to explainability and interpretability. So what are they? There's lots of different definitions of explainability and interpretability. These are fairly common ones in the literature, but lots of different ones. So I don't want to give the impression that this is the be-all, end-all. But an explanation refers to a collection of features that have contributed to produce a decision. By contrast, interpretability aims at revealing models' properties in understandable terms to the user. So this example down here is an example of an explanation. So this histology slide was used in a classifier, and this paper looked at attention maps that determined where the classifier was looking in order to make the decision. And they compared their approach to the original approach, and they said, well, this original approach doesn't really help you much because so much of the image is salient or important to making the diagnosis. They had a much more focused area of attention, and that seems great. But particularly for vision models, but for many things, it's very hard to know exactly how helpful that is in understanding what's going on under the hood. This image from Cynthia Rudin is a nice illustration of this. So even if you know exactly what the algorithm is looking at and is determining whether something is a Siberian Husky or a transverse flute, it might not mean anything to you as a human being. This isn't always the case, given that you just saw an example earlier on about the chest x-rays, where if it's looking at the laterality marker, you know that that's something important. But if you just have kind of the center of the image highlighted, very hard to know exactly what's going on. So how can we get around that? Well, people have been, especially in the past year, have been doing the slow, laborious work of really looking under the hood of deep neural networks. So this paper from the OpenAI group is what they did was they looked at Inception v1. And so Inception v1 is an image classifier that was trained on the ImageNet database. So that's a database of millions of public images from the internet that were manually labeled and has been used as a benchmark in vision or in classification for a long time, for several years now, for sure. And what they did was they looked at neuron groups, and they created what they call feature visualizations. So these are images that highly excite these particular neuron groups. They found in the first layer Gabor filters and color contrast detectors, which wasn't really news. Like this has been known for a while that these Gabor filters, which check for edges and orientation of edges, and these color contrasts, which check for color contrast, have been known to be present for some time now. And interestingly, these actually match a lot of the way that biological vision is done in brains. But what they did was they went further with this. They looked at some of the later layers, and they found more complex features emerging. So they found these sets of neurons that would detect boundaries, curves, and even starting to get into like really weird things. Like they found ones that detected eyes and eye-like features and these strange proto-heads. They often look like dogs because a lot of the ImageNet database had a lot of dog pictures. And so there's also like neurons for fur and fur orientation and sort of weird things like that. But I thought it was really fascinating that these authors are really going under the hood and looking at how some of these algorithms actually work down at like the neuronal level. I wanted to touch on one more paper from the OpenAI group that I thought was super fascinating. This one is very recent, maybe like a month or two ago. So the concept of multimodal neurons has been known for some time in biological neural networks, i.e. brains. If you stick an electrode in someone's brain and you show them a picture of Halle Berry, a sketch of Halle Berry, and the text saying Halle Berry, you can find single neurons that respond to this concept. And so the OpenAI group has created this CLIP network, which is a vision model that has been paired with a language model. And it aligns these pairs of images and text. And they found that more than just aligning them, the network itself has created these multimodal neurons that will fire in response to specific concepts. So if it sees a panda, or if it sees the text panda or a sketch of a panda, it'll fire the same neuron. It'll give you some confidence. I want to bring up the concept of adversarial attacks for two reasons. Number one, to highlight the brittleness of some of the neural networks and machine learning models that exist. If you look at each of these two images, they're very clearly pandas. But this one on the right here has had some, what looks like just straight noise to a human being that has been added to it. And what you can do with this type of adversarial attack is you can go from a relatively high confidence in the correct category to a very high confidence in the incorrect category via the addition of this noise. It's not exactly noise, like this has been mathematically optimized to make it say gibbon. But this kind of highlights the brittleness of neural networks. And a very interesting thing about adversarial attacks on the CLIP network is here, the non-adversarial picture is correctly identified as a Granny Smith apple. But if somebody just like labels this iPod by writing on it, it all of a sudden has extremely high confidence that this has become an iPod because it's associating the concepts together, which I thought was super interesting. So like, what does this mean? What does this mean for medical AI and for the future of things? Well, it does show significant promise in being able to look under the hood of some of these very complicated algorithms, some of the most high performing ones like the deep neural network, convolutional neural networks that are doing image classification, for example, and really opens up the promise of understanding exactly how they work and slowly turning them into more interpretable models. Also, an interesting application is that we might be able to learn more about and potentially create analogs of biological neural networks like brains and neural tissue. I think we're going to see some convergence of biological neural networks and artificial neural networks more and more as time goes on. All right, moving on to privacy. So let's say you have a data set of, let's say it's 10,000 chest x-rays, and you have, so you have 10,000 patients, you have their names, you have their ID numbers, and their comorbidities, you have their age, and some lab values. And you want to release this data set publicly on the internet so that other researchers can write papers on it and can make their own machine learning models. It sounds great. Without going to each of those 10,000 patients and getting their permission to put their health data in public, which there's no way you would be able to do, and I think a lot of people wouldn't want that for good reason. How can you do this? How can you do this in a privacy-preserving way? So the first idea that you might have, well, maybe you could anonymize it. You know, we're going to get rid of all of the ID numbers and names, and then we're going to release the data set. Like, will that work? No, won't work. An example of how this can fail, you guys might remember from kind of the mid 2000s, Netflix had a prize, a contest for improving their recommendation algorithm. And they released 100 million movie ratings from like 400,000 users. And the users were anonymized, but this group found that they could look at those Netflix movie ratings, they correlated them with public IMDb movie ratings, and they found associations, and they found fairly strong associations, and they were able to de-anonymize a lot of these Netflix movie raters. And that was like a bit of a turning point in some of the privacy literature and the way things have been moving since then. Things picked up quite a bit around this point, sort of the 2008 type of thing. So what if instead of anonymizing, you're going to only release aggregate statistics? You're only going to just pool everything together, and then people can only query this aggregate. You know, surely that's going to be foolproof, right? No. Unfortunately, won't work. Very interesting study also from 2008 that looked at when you have a big batch of DNA that you've contributed 1,000 individuals' DNA have gone into it. So 0.1% from a single person. You can identify that 0.1% very consistently based on single nucleotide polymorphisms. You're able to statistically recover who the person was from this 1,000-person batch. So unfortunately, not provable. Maybe aggregation will work in some cases, but it's not going to be a silver bullet. How about you give up on releasing the data set, and you're just going to release the model? Okay, surely that can be okay, right? No, unfortunately. So if you train a text generating machine learning model that predicts the next character or word in a sequence, and you have it on a really big corpus of text, let's say from the internet, and you type in "my social security number is" as your prompt, and you have it predict the next character or word, you might get someone's social security number. These models do a lot of memorization, and a lot of this is going to be related to overfitting, but not necessarily. You can have a very accurate model on real world data sets that isn't significantly overfit, that still has memorized a lot of information and potentially sensitive information. Okay, so how about instead we use math? Yes, this is the answer. So there's this concept called differential privacy, which really what it's doing is it's limiting the impact that a single individual can have on the output of the model. So for two neighboring databases, D and D prime, neighboring meaning they only differ by a single record or a single person, it limits how much the model output can change. It's bounded by this epsilon value. So it turns out this does work well. The original usage of differential privacy, and it's provable, it's mathematically provable. The original use case for differential privacy was where people would have their potentially sensitive information go into a trusted database, and then the public would make queries on this database, which would go through a sanitizer. And the sanitizer would provably keep people's private data private. So this concept of differential privacy has been extended to more than just making single queries to databases. There's been a lot of work in applying this to machine learning. This was an interesting paper where this group looked at sharing data from medical trials, similar to what I was talking about before. So it's difficult. It's difficult to provably keep people's private data private in such a way, like especially with medical data. Very difficult to get ethics data sharing agreements to release data sets. This is one of the reasons that it's so hard to get large data sets to work with. So their solution, how about we generate synthetic data using what's called a generative adversarial network? You might have heard of generative adversarial networks. This is a super interesting website that you should all look at. How is it proven that differential privacy works? There are properties of differential privacy that the proofs are they're not too bad. I think I might have some of the references on my reference slide, but I could, if you email me, I can send you a list of some of the mathematical bases for how differential privacy will provably keep people's data private under certain conditions. So for example, if you chain requests together, it still keeps it private. If you do requests for data from multiple people, it can you can prove that that's going to continue to keep their data private. It really is a good way of mathematically bounding it. I'm not going to go through the proof right now, though, sorry. So these generative adversarial networks from thispersondoesnotexist.com is exactly what it says it is. These people don't actually exist. These are generated by a machine learning model to look as convincing as possible. But you can see how like, for example, certain features are probably taken exactly or almost exactly from people. And so you could see how this might not be totally private. Like this mouth probably belongs to somebody recognizable. And so this paper, they were looking at creating the synthetic data using a generative adversarial network, but this can still reveal sensitive data. So what they did was they trained this generative adversarial network with differential privacy. And so this was from the SPRINT trial, which is a blood pressure therapy trial where they compared standard to intensive blood pressure management regimens. And they created these private data sets that matched the non-private data sets quite well. And in fact, can certainly be used for other machine learning purposes or could be used for other types of research. I thought this was a really interesting way of kind of getting around the problem of data privacy in medical data. All right, future of AI. So I'm hoping to get a little bit of discussion here because I could talk about each of these topics for like hours and hours and hours. But like the long and the short of it is that the AI winter of the 80s and 90s is officially over. There is foundational work being done at least every month. You'll see a new paper that is showing something critical and something in sort of the basic science of AI research. Things are moving forward, and there's lots of foundational improvements being made. For example, I thought this was super interesting. There was a paper I saw that looked at so back propagation in neural networks is a way to train them. You look at the output generated by the neural network, and then you propagate the error between the output and what it actually should be generating, and you propagate that error backwards, and you use that to change the weights in the entire network. This concept can't be done biologically. The causal chains are too long to do it reasonably in a biological system, like in a brain. And so people have actually learned how to create neural networks with machine learning that act only locally. And this may in fact be a way that human beings and other animals learn using their brains. And we're really starting to push things further and further, closer and closer to human level or beyond performance in lots of different tasks. Some of the really, really big things that have happened recently, AlphaFold was absolutely enormous. So this is the protein folding problem, meaning if you're given a sequence of not nucleotides, of protein monomers, can't think of the word, anyways, and yes, amino acids, thank you, Shane. A sequence of amino acids, can you predict the 3D structure of the protein that will ensue? And AlphaFold was an absolutely enormous leap. Like it just destroyed all the competitors and all the prior curves of how things have been improving up until now. GPT-3 is a language generation model developed by OpenAI, which creates some absolutely incredible stuff. So there's incredible advances being made, but even if everything were to stop right now and there were to be no further advances in any of the base AI algorithms and math that are being done, there are tons of low-hanging fruit, particularly in the medical field, that could be picked and that you can make things out of. Using just off-the-shelf existing tools, there's an enormous amount of value that can be made, particularly in medical AI. That is it for my presentation. I'm really hoping that we can have some questions or some chat or something. It's a fairly small group, so don't be shy. And I'm going to keep these up for a few seconds so they make it onto the recording. And people can look up the papers if they wanted to look them up. Oh, thank you. AI winter refers to a period in the 80s and 90s, and honestly early 2000s, where there was virtually, well, not virtually no, but much less enthusiasm and work in artificial intelligence. There was a lot of enthusiasm for artificial intelligence in kind of the 60s and early 70s as people first started working on the problem. And then they found that it was much harder than they initially thought it to be. And work stagnated for decades, really up until a lot of the machine learning, the modern machine learning techniques were discovered and propagated kind of starting around 2012. 2012 was when the first really high performing machine learning models were deployed on the ImageNet database. It started working really, really well. And things have only ramped up since then.
Can I unmute myself to ask a question?
Yeah, go for it.
So you talked quite a bit about like privacy and all the problems when we try to privatize our data, but now I'm curious, like how would you be able to maintain privacy effectively? Is there a way that people have been or companies have been doing this effectively thus far, or is it just an ongoing problem?
It's mostly just a problem. So I don't know of any of all the places that I find like public databases of medical information on the internet. None of it has had differential privacy applied to it. And so presumably using some of the attacks that I mentioned, you could use those to go back and like re-identify people, which would be really awful because then we might lose data, like the few data sets that exist. But there are ways mathematically to protect this information, at least better than it is, with low or at least bounded decreases in accuracy. And so there is a way forward, but there's like a lot of loopholes and caveats to that.
Okay, that makes sense. Thank you.
You're welcome.
Hi, can I just ask a question as well on privacy?
Yeah, of course.
So how good are these when you sort of convert data and make it private, if there's a good enough computer program out there that actually can decode things and reverse it, or you think this is just impossible the way you actually manipulate the data to make it private? Is it really that good? Is it?
Do you mean that good at protecting the privacy or at like preserving the accuracy?
Well, both, right? I presume the whole idea will you make it preserving the accuracy of the data set, right? And you make it private.
Yeah.
But there must be so you must be manipulating something in the data and make it private, and so and then there's no way of reversing that if you have a something other because obviously there's a lot of hackers out there, right? Who obviously are very clever at reversing this sort of algorithm that you design to manipulate your data and make it private. So yeah, I just wonder how good it is in making it private, and presumably it is fairly accurate. It's still representing the original data set
yeah. So the way that differential privacy works, and a lot of the related ones have sort of added on to differential privacy, is that you add noise to individual aspects of the data set in different places. So the original differential privacy would add noise to the responses to the queries that you're giving back. But extensions to differential privacy have added noise to, for example, the gradient that's computed in a machine learning model, or you can add it to the weights of a model in different places. And obviously this noise has a cost to accuracy of the model. You're adding noise. You're certainly not going to improve things. So there is a trade-off in how much noise you add versus how accurate the model is. And then, however, you can imagine that if you add more noise, it becomes more private. So the trade-off becomes how private do you want to be versus how accurate do you want the model to be. In practice, you can make things fairly private. At least you can give it a number. You can say it's epsilon differentially private, and then you can report your accuracy, and the accuracies tend to be quite good with relatively low privacy levels. Part of the reason that that the performance is still pretty reasonable in the machine learning models is that there's like a close relationship between overfitting and privacy. So if you overfit the model enormously so that you're just memorizing the data points, you're going to perform worse on test data sets. And if you overfit and you memorize lots of data points, it's also going to be very, very much not private. So sometimes, so that by adding this noise, it's kind of like performing some regularization, and you can you don't have as much of an accuracy loss as you might expect. Okay.
Thanks.
No problem. How did AI researchers figure out what the AI, which false connections the AI was assuming? Which one are you talking about for the false connections? Is this the X-ray data set, or the one that was looking at the taking the deep dive on Inception V1? The X-ray data set. So they were looking at the, hang on, let's see if I can. Just bring it up. They were looking at the saliency map. So as I said, it's crude, right? Like if you knew that it looked just at the chest here, at the lung fields, you wouldn't really have any idea how it's working. But because you know that it's looking at the little laterality marker and the fact that it says portable here, and you know that it's assigning importance, like it's using these areas to make the diagnosis, you can at least guess that the model is using these and is making the decision strongly based on these factors. So yes, there absolutely is some guesswork involved in this. The paper, they kind of went into it a little bit more, and they tried to characterize things a little bit better. So what they did was they made a network where then all the network did was it just predicted which hospital the X-rays came from. And this model had like ridiculous accuracy. It was like 99.95% accurate or something. And then what they did was they artificially altered the prevalence of pneumonia in the different hospitals. So they changed it themselves, and then they had a look at the accuracy of the model. And the model works best when the prevalence of pneumonia is the most different between the two data sets, which makes sense because then the model can immediately know which hospital it belongs to. Like they proved that that's not hard for the model to do. And then it can immediately change its guess for how likely it thinks a particular X-ray is going to have pneumonia or not. So there were a few different ways that they kind of intimated that that this is what the model is doing, but they didn't prove it. What is noise? So noise is like a random an element of randomness that is added to the data set, or added to a particular data point or a particular part of the model, for example. And so noise, if you add noise, like some random amount, you won't be able to recover the original data point. If I roll a dice and it says a 3, and then I roll another dice and I add the first one, the second dice to the first one, and then I just give you the number of both of them together, you're going to have a much tougher time guessing the first one based on the number of them together. So you could say that the second die roll is noise.
So what do you see is the future? Oh wait, that default is the follow-up question.
Oh, one more. Noise is used to protect our data. That's correct. What is a reasonable amount of noise to add? I can't remember some of the default kind of epsilon values that you would use, but it depends on the query. It depends on the model. So you can imagine that in certain questions are going to give away more than others. If I just ask for a count of how many people had cancer, and I'm going to spit back a number, the contribution of a single person whose privacy you're trying to maintain will only change that number by 1. Either they're in the data set or they aren't. This is referred to as the sensitivity of the query. If you instead want to create a big graph that shows how many people of each different type of cancer there are, that number could change for every single bar in the graph. And so the amount of noise that you would have to add to such a big query like that is going to be more than for other queries. So the amount of noise will change depending on what you're trying to get out of it. This is a limitation of differential privacy, and it certainly makes things hard for non-numerical queries. People have done a lot of work in this regard, but the problem's not solved, and there's still a lot of there are still holes in privacy. Sorry, what was that, Shane?
So as a surgeon, what do you see the future of AI in surgery? What are some of the low-hanging fruit there?
Oh, awesome. So things that I expect to see lots of work in AI going forward. There will be lots of work in sort of ancillary fields to surgery. So there will be lots of work in radiology, pathology. We'll have huge advances and huge benefits from AI. Lots of, again, regarding ancillary fields, lots of hospital work. So things like intensive care units, but even just patients on the ward and monitoring is going to improve. And there's going to be a lot of research coming from those areas. Robotics will start to benefit from AI in surgery and will gradually make their way in, but I think that will take a while. And I do predict that we'll see slow advances. You'll see some foundational work in computer vision for like laparoscopic surgery, for example, and it might eventually move forward to having like robotic camera operators or assistants. I do think that the era of a robot performing a surgery unsupervised is many years off, like certainly decades off, but that'd be pretty cool to see at some point.
Yeah, thank you.
All right, well, if there are no other questions, I just want to thank everybody again for participating. I do appreciate the discussion. That was a lot of fun. Yeah, I'd like to thank Shane and the entirety of Ames for putting this on and for inviting me. Thanks very much.
Yeah, thank you, Scott, and thank everyone else for joining in our pilot project here, this AI in medicine curriculum. And this concludes our lecture series, but we do have 2 more workshops coming up, one on Wednesday, and that'll be using AI to diagnose pneumonia. And week after that will be maybe an easier workshop for some of you at how to read through and critique an AI in medicine paper. Hope you guys join us then. And I'd like to thank all of our speakers, and thank you again, Scott.
Thanks, Shane.